So let's continue with the discussion that we had in the first part of this video, and I'm going to um, now talk about how the vector dot product. So just a quick recap: you have any two vectors and you can define an operation on them called a scalar dot product, and we emphasize the word scalar because we're going to get the answer as a number, and this number will be equal to the modulus of A plus the modulus of B into cos of the angle between them, and this is the scalar dot product. And we said last time that we need to convince ourselves that A dot B is equal to B dot A, and this fact will be exploited when we do the calculations. And then there is another important product which is called the distributive product of the distributive property of the scalar dot product, and this will again play a role in the way we simplify or make our calculations more efficient. Now, just want to quickly remind you how we realized the importance of resolution of vectors in the coordinate system, and the resolution of vectors in the coordinate system can be attributed to the addition operation of vectors. Okay, and then the properties of addition operation were beautifully exploited. That is, the fact that A plus B is equal to B plus A was beautifully exploited, and the associative property also. A plus B plus C plus D does not need any brackets. No brackets are required. Now this was exploited to use to make the addition and subtraction of vectors very efficient. We used to call it the resolution and addition of vectors. Right. Now just want to remind you about this proof. It's okay, this is A and this is B. The fact that this is A plus B was a definition of what is vector addition. So this was what I have written here is the definition. Okay, and what is the corresponding thing in the dot product? It is this step. So this is the definition. This step is the definition of the dot product. Then we said, okay, let's do B plus A, and that would go like this. This is B, and then up, and then any two parallel vectors of the same length are the same because they have the same direction and magnitude. And then you do A. So you do B plus A, and you get, and you use the definition, and you get the same answer. So A plus B by the definition is the same whether you do A plus B or B plus A, and that is this is a valid proof that this is true. Now if I remember correctly, I said you could think of a similar graphical proof for associativity, but it's not worth the trouble. Maybe okay, you can find it in some book, I'm sure. So can we give a proofs for the two important properties of scalar dot product, that is that A dot B is equal to B dot A and A dot B plus C is equal to A dot B plus A dot C. Now this one is very easy, so I think you'll find it in most of the books in a one-step proof. It depends a little bit on your trigonometry. So A dot B is equal to mod A mod B cos theta, and B dot A by the definition is mod B mod A. Remember that mod A and mod B are scalars, into cos of 2 pi minus theta, which happens to be cos theta, and therefore it happens to be cos theta into mod A into mod B. That is because cos of 2 pi minus theta is the same as cos theta, and you're done with this part of the proof. Now this one is more graphical and much similar and as almost as simple as a plus b is equal to b plus a. I have a picture here, and I just want to keep the picture on for a few seconds. You can pause the video here and look at this picture for some time. I think I've taken it from a book uh, called Borisenko and Borisenko, I think, and Tarapov. Please don't worry about the rest of the book, or I think this picture is all you need. So it's a picture proof of the fact that the distributive property is valid in a dot product. I just realized that you need a little bit more background to understand this proof. Okay, so one of the interpretations of A dot B is equal to mod A mod B cos theta is to interpret B cos theta as a projection of B on A. So let's just tell you what it means. So this is A, and then you have B, and then you have theta. Then you drop a perpendicular of this vector, perpendicular mind you, on this along the line A, and what you will quickly agree is that this length is B cos theta, and this is also called, and that you have to multiply by mod A to get your dot product. So in other words, this red length is important, and that is what decides the dot product. So can you so I just see that there is this construction being made here. This is the perpendicular, this is the perpendicular, and I think that's about it. I have a feeling that with this background you'll be able to understand this picture proof. So we're done with the proof. You can pause this video at this time and review the proof. I shall tell you how it's exploited in calculations now. This is now getting really easy. So you start with saying that somebody needs to tell me what is A dot B, and then I say, look, I know this trick already. I choose a coordinate system. So more and more now you're realizing that the coordinate system will help you to make the calculations very systematic and very clear, and therefore you will not make any mistakes. So the first step is to write A. Let's do 2D for today. Write to A as AXI plus BAYJ, and you already know what this means. We spent a lot of time on this. B as BXI plus BYJ, and you know what it means. And now I have to, this step is the first step. Now you can't, now it's more and more clear that the resolution of vectors that we have learned is extremely useful. Now we are going to say that I'm gunning for A dot B, which is the same as AXI plus AYJ. Quick reminder that these are scalar numbers. Please remember that they are scalar numbers. We've repeated that aspect numerous times. Plus, it's important for you to do some numeric examples so that all these ideas settle in your mind. Now here's where I use the two properties of vectors. I'm going to use upfront distributive property. So I'm going to write this as, this is one vector dotted with two vectors. Okay, so just to tell you, this is let's say this is capital A, and this I'm calling it capital B, capital C. So essentially I'm saying that, can you tell me what is A dot B plus C, and then this is going to be A dot B plus A dot C, which translates to AXI plus AYJ dotted with BXI plus the same thing again, A, which happens to be AXI plus AYJ, okay, dotted with C. C is, according to me, this vector called BYJ. I hope this is clear enough, because I'm going to continue from here on the next page. So I have clearly used and exploited the distributive property. Mind you, this is going to lead to a very simple result. So please stop for a minute and pause and see the contribution of the distributive law, which we have proved. So let me just keep going now. So I'm going to repeat the step again. It's worth repeating it. AXI plus AYJ is being dotted with BXI. Quick reminder, AX, AY, BX are all scalars, plus yeah, and then the same thing again, AXI plus AYJ is being dotted with BYJ. Now I could just for your convenience, okay, this is unnecessary overkill, but it's all right. So I'm going to switch now, and I hope you realize that I'm using the commutative property. I think I'm calling it an overkill, but actually it is required to be as rigorous as I'm trying to be. So you please note that I'm now using this second property of dot product, which is the commutative property. Alright, then I use the distributive property all over again, because I have one vector here and two vectors here, and then I write this as BXI dot AXI plus BXI dot AYJ plus BYJ dot AXI plus BYJ dot AYJ, and now this part is mod BXI mod AXI cos of the angle between I and I, plus so on. I'll leave it to you. I think these two terms will go to 0, because cos of the angle between I and J is 0, and that's because the angle between them is 90 and cos 90 is 0, and this cos here is cos 0, that is 1, and this cos here, that is between J and J, is also 1, and this is clearly AXBX, and you'll get another term from here, which is AYBY. So let me summarize. What have we proved? If you have A dot B as your goal, first see whether A is available in the resolved form. Okay, and then if B is available in the resolved form, alright, and then the answer is directly equal to AXBX plus AYBY, which is clearly a very compact and fantastic calculation aid. Now let's not forget what this means. This is also equal to mod A into mod B into cos of the angle between them. And also remember that mod A is something that we've learned. I hope you have not forgotten. Mod A can be easily gotten from here. It's just equal to square root of ax square plus ay square. Pretty much the same here. Mod B is square root of ay square plus by sorry, I'm sorry, bx square plus by square. And then finally we do have another result which is not to be memorized because it's pretty obvious where it is coming from. I think I am, yeah, is equal to root of ax square plus ay square plus root of bx square plus by square. Sorry again. Into. Okay, no mistakes here. Into cos theta. All right. This is not something to be memorized. The only thing, this is just a quick application of what we have learned. What you need to memorize is this. And there isn't, it's so symmetric that it's hard to forget it. Okay, and please, as a final quick reminder, where did we get this from? We got this from, I would say, the story starts with resolution, which we got from the properties of vector addition. Okay, and properties, mind you. I'm not repeating these properties again. Next is, we got it from the dot product. The dot product, the result for the dot product, I think we got it from the properties of the scalar dot product. Okay, so these are the contributors, the properties of the scalar dot product and the properties of vector addition, for which we have proofs. We have proved them, not associative, but it's all right. You can get the associative proof as well in your textbook. But these simple proofs lead us to the calculation aids. And it's time for you to solve a few examples in your textbook. Go for the solved examples, but these are very easy, and you should use them all the time for your calculations. In the next video, I'm going to talk about the vector cross product, which is a little bit more involved, just a little bit more, but of immense use in simplifying the calculations in the next chapter, that is rigid body dynamics.